this is Dr. Beck with another Chemistry GCSE video in the AQA specification. This lesson is all going to be about metals and metal alloys. You are going to need the things listed on the screen. You will not need a calculator or your phone, so please ensure your phone is away and off so it's not going to cause you a distraction. For this lesson, you'll also need a degree of imagination, and we're going to use a nice little model of metals and their atoms and how they are held together in a structure. First of all, could you please have a go at this starter task, what we call a do now task. Here we see an element symbol, as you would do on a periodic table. I would like you to have a go at as many of these questions as you can, writing down the answers carefully, drawing diagrams carefully, and using keywords for descriptions. So when you're ready, pause the video and come back to me when you finish as many of these as you can. Okay, hopefully you didn't find that too difficult. Let's go through those answers. So if we look at our periodic table, we'll see this towards the top left. This element is called beryllium. It is a metal. Using our knowledge of those numbers and what they mean, that tells us there are 4 protons, 5 neutrons, and 4 electrons in this atom of beryllium. Those electrons are arranged with 2 in the first shell and 2 in the second, so there will be 2 shells in total with some electrons in them, and therefore 2 electrons in the outer shell of this atom. What group is it in? It is in group 2. Now we can find that out from the periodic table, but we can also find it out from these numbers, this symbol, because we can work out that it has 2 electrons in its outer shell, and we say that for the first 20 elements, the group number tells us the number of electrons in the outer shell. And finally, the number of shells tells us the period. So here we've got 2 shells with some electrons in, so this will be in period 2. Well done if you got all those right so far. So I gave you a symbol for oxygen and how that forms an ion. Let's do the similar thing for beryllium. So we start with a picture, a diagram of the atom. Now you may have drawn crosses. You may have drawn circles, doesn't matter. You may have drawn those circles or crosses in slightly different positions. Again, that doesn't matter. The principle here is for the atom, there are 2 in the first shell and 2 electrons in the second shell. So this is a metal, and as we know, metal atoms want to lose electrons. That's going to make them more stable, and in doing so, they're going to form an ion. So therefore, here is a picture of this happening, and we end up with this ion symbol. We don't need the square brackets. It is a useful thing to do. Sometimes the mark scheme says add them, often it says don't, but what we will need is an accurate picture of the beryllium ion and the charge. In this case, it'll be 2 plus or 2 positive because it has lost 2 negative electrons. Well done if you got that right. So, a beryllium atom will lose 2 electrons, and in doing so, it's going to form a beryllium ion, and this will be Be2+. When this element reacts with oxygen, it makes an ionic compound. We've already given you the oxygen symbol for the ion formation, so the oxygen atom will gain 2 electrons to form an ion. Now this one, we change its name, it is oxide. So not oxygen ion, oxide, we change its name, we shorten it, we add IDE at the end, and the symbol for that is O2-. And hopefully you can see we've got 2 positive charges and 2 negative charges. These things will then come together, 1 ion of each, to form beryllium oxide. So therefore simply the formula for this compound is BeO. If you need to pause to recap, to go through those ideas, this potentially would be 4 marks for a GCSE paper, and the key parts of it are underlined. Here then is a summary of that. This is beryllium oxide. This is a picture of this white crystalline material, BeO, and those are the ions shown in detail. So well done if you got all those correct. Remember, all of this information can be taken from the periodic table, but also then using your knowledge of electrons, shells, how ions form, and then how ions interact. Let's move on. Today's lesson then is going to be about metal and metal alloys. So please, could you please make a note of our learning objective and then write down the key words and then have a think. What do you know from your previous studies about metals? Pause the video and come back when you're ready. Great. Hopefully you've been thinking about metals, excuse me, and the structure and properties of metals. You may well have done in a previous year, probably before GCSE, little tests with different materials, including this one. This is a nice test which demonstrates that metal objects such as coins conduct electricity. Now today we're hoping to explain why they conduct electricity, and we're also going to look at the things our coins are made of, and again, why do we choose those materials? Here is our periodic table. On the left-hand side, all those grey-blue elements are metals, and the ones over to the right are non-metals. The pink and the yellow colours there. And we should know by now that metals, their atoms, want to lose their electrons to form a full outer shell. The electrons in the outer shell become what we call delocalized, which means they're then free to move, leaving a positive ion behind. The positive ions can then be attracted to the delocalized electrons by what we call an electrostatic force of attraction. What does that all mean? We're going to come and look at a model of this, but fundamentally those metals want to lose their electrons in their full outer shell, to form a full outer shell. So we call those the outer shell electrons. They want to be lost and then they can become delocalized. Let's just recap. Without looking at your notes from previously, here is beryllium. Here's a symbol for beryllium. Can you please now just draw an electronic structure diagram of the atom of beryllium? Use this to help you. Pause the video, come back when you're ready. Excellent. Hopefully, if you didn't use your notes, you would have got something like this from memory. Well done if you did. If you needed your notes, well, that's okay. But I would like you to become more used to using these numbers and understanding what they mean. So this is a group 2 element, and you can see we have an atom of beryllium with its 2 electrons in the first shell and 2 electrons in the outer shell. Now these last 2 electrons are the electrons that the beryllium atom wants to lose. And by losing them, they become delocalized. They're not lost in this particular case if they're in a metal structure. We'll fill in the details in a second. If you're interested, beryllium looks like this. It is a typical shiny grey metal. Quite dense, very useful, but it takes this form of solid at room temperature. So this should tell us some clues about its physical properties, whether it has a low or a high melting point and boiling point. Okay, now we're going to have a look at why metals have the properties they do, why they are hard, why they are usually solid at room temperature, and why they conduct heat, and in particular why they conduct electricity. So we're going to use a little model. The model I'm going to show you is using biscuits. So this is where you need a bit of imagination. Here is a biscuit. It tells us it's a round biscuit, which is very useful. But this is our picture of an atom. However, from what we've discovered so far, if this is a metal atom, we can consider it as being a central positive ion And in the case of beryllium, we can think about the two outer shell electrons. So we can consider it then as having these two outer shell electrons and a central nucleus. We call that left behind the ion. And this is going to be an important picture for us to use for our model. Okay, now I'm going to try to simplify the model. I'm going to take away one of those electrons. Perhaps it's a group 1 atom now. Perhaps it's lithium. Perhaps it's sodium. Perhaps it's potassium. Doesn't matter. We're going to use this idea for our model. So to keep it simple, we're going to just use one delocalized electron from this outer shell of this atom. So to recap, here's the central positive ion and the outer shell electron. Let's add some more metal ions. So again, we're going to use this model. And to show the positive charge, I've put a cross, a plus sign on these metal ions. Now remember, each one of these is going to have a delocalized electron. So to begin with, I'm just going to put those on there, 9 to begin with in the total. Now, what do we mean by this word delocalized? Well, what we mean is these are free to move. Yes, they are attracted to the positive ion because they themselves are negative and opposite charges attract, but they are going to be moving around and through this giant structure. We call this a lattice, a giant structure, a little bit like the ionic lattice, but different in many ways. These things are moving. They're not associated with any one atom or ion. They can move between and around and keep swapping, and they can hold the whole structure together. There is an electrostatic force of attraction between a positive ion and an electron, and between the electron and the next positive ion. And again, these are delocalized, they can move around. Now, this is a nice picture of the structure of a giant metallic structure because it gives us clues as to its properties, its structural and physical properties. First of all, these ions form a regular structure of layers. Hopefully you can see that in a pure metal, these layers are free to move past each other. And as they're doing so, they are not disturbing the rest of the material, the rest of the structure. I can push one of these layers and it's fairly easy to do that. Now this explains why metals, pure metals, bend. We say they are malleable because we can slide these layers past each other without disrupting the rest of the structure. So if we imagine say a spoon made out of iron, it will be fairly easy to bend. And similarly, pure metals are very malleable because they have this structure which allows those layers to move or slide past each other. Now, the second thing this model helps us to understand is how metals conduct electricity. Remember, these are green sweets. These are our electrons. They are charged particles. Now, if we put them in an electric circuit, then these are pushed through the material. They're replaced by other electrons coming in from the side, but those electrons continue through carrying the charge. Okay, and here comes some more electrons from that battery or cell. And we say then this movement of charge is electricity. This is the current. So because they are free to move, they can move, if we put it into an electrical circuit, through the structure. Yeah, it's important we say through the lattice or through the metal or through the structure. And here we go. They are delocalized, they can move and they can slide all the way through. And also this helps us to explain how heat, thermal energy, is conducted through metals, because these electrons can become excited, they can become more energetic, they can move quicker, and they can bounce into, if we started to heat this end of the material, they were moving really quickly, and they're crashing into all these other electrons, and that energy will dissipate very quickly through the material. Okay. very quickly that energy will be passed through the material because these electrons are moving and are more energetic and are crashing into other electrons and transferring that energy to those other electrons. Okay. What I would like you to do next then is to draw a diagram of a metal based upon the one I'm going to show you next. And then could you please, once you've sketched a neat copy, add these labels or draw lines from the words to the different parts of the structure. So here is the diagram. I'd like you to sketch as neatly as you can, and then please add those labels or add arrows to the different parts, different features of that structure. Pause the video when you're ready and come back to it to check your answers. Okay, welcome back. This is the kind of picture you might see in an exam, and you need to understand what's going on. So let's go through those things one by one. The metal ions, well, there are lots of them, and these are the large positive charges we see here. Any of these are metal ions. I've labeled 2 here. Delocalized electrons are these here. I've just labeled 3. You may have labeled 1, maybe 2. I've labeled 3 here. Now the layers, well, there's one layer here, there's a second layer below, and a third layer at the bottom. We can label those simply with the different layers. Here we've got 3 different layers. The whole thing is a giant structure, a repeating pattern of these charges over and over and over again, forming this large structure, the metal itself. This one's a little bit tricky, but the electrostatic attraction between the charges, I'm going to add these arrows here, positive and negative attract each other, positive and negative attract each other throughout the material. Okay, and this is kind of like a glue holding the whole thing together. A strong force of attraction between these opposite charges, the positive ions of the metal and the negative electrons. We're talking here about charge. So pause the video to check your work, and when you're ready, move on. Can we use those keywords now? Can we put them in context? What I'd like you now to do is to explain using keywords how the particles are held together in a metal. This in an exam paper might be worth 2, 3, perhaps 4 marks if we include ideas of the structure of the metal. So I'd like you to use as many keywords as you can to explain how the particles are held together in a metal. Pause the video, come back when you're ready. Okay, hopefully you've used those keywords. Hopefully you've written something like this. First of all, the keywords are underlined. We have electrostatic force between atoms or ions and the electrons to form a giant metallic lattice. Check your answers, check your work. It is interesting here, I've said atoms / ions. Technically they are ions, but in a mark scheme, particularly for trilogy science, either is accepted. Okay, I would personally prefer ions, but it doesn't seem to be important for the mark scheme. They technically are ions, so please, I would aim to use that word. Metals have properties that they have in common, and these are chemical and physical properties. First of all, the physical properties, the 4 you need to be aware of, is all of them have high melting and boiling points. Now, when I said all of them, there is one which is liquid at room temperature, mercury, and there's a few others which are unusual, but in general they are solid at room temperature. This is because of the electrostatic force of attraction between the delocalized electrons and the metal ions. Now that force is strong, and multiplying millions and billions of times in a metal structure, the metal itself will be held together with these strong electrostatic forces of attraction. So metals will have high melting and boiling points. Some metals melt at over 1,000 degrees Celsius. The second property you need to know about is they are malleable. This is a great GCSE word. This means we can bend and shape them. Because these layers of ions can slide past each other in a pure metal. The third thing we've discussed, and the third thing you need to know about, is that they're all conductors of electricity, excellent conductors of electricity, because the delocalized electrons carry charge through the metal, through the lattice, through the structure. Let's have a quick look at an animation of that happening. Hopefully you can see that the blue dots, the delocalized electrons, are buzzing around. They're constantly moving. Some are moving up and down, some are moving left to right, right to left, but in general, hopefully you can see in this electrical circuit, in general, they are moving from left to right. And this is then the flow of charge, which we call current. And this also explains our final property. Metals are good conductors of thermal energy because energy is transferred by these delocalized electrons. If we heat up one end of a metal bar, the electrons there will become excited, they will start to move faster, they will gain energy, have higher kinetic energy, their velocity, their speed will increase, they'll crash into other parts of the material, and very quickly that thermal energy will be transferred through the whole structure. Okay, so to begin with then we have talked about the bonding within pure metals, and we've used many of these key words we see here on the right. Let's now have a look at metal alloys and what that means. Most of the things in the world around us which are made of metal are made of metal alloys. As we've already discussed, pure metals are soft, and they will be too soft for making something like this aeroplane that you see on the screen in front of you. So this will be made of a mixture of different metal alloys. There'll be some different metals for the wings, maybe some little metals for the window frame there you see in the cockpit, for the fins of the tail, for the front, but they will all probably be metal alloys. So what does that mean? What do we mean by alloys? There's a clue here with a picture. Again, this is something you may see in an exam. We're going to go back to the model using our biscuits. First of all, you need to know about 3 alloys. First alloy you need to know in your GCSE is one we should be aware of called steel. Now, steel is a mixture of carbon and iron. So iron is a metal, and you'll notice here carbon is unusual, it's a non-metal. But steel is a mixture, and this is what alloys mean. Alloys are mixtures of metals or things like carbon. Stainless steel is a type of steel which is more resistant to water. It doesn't go rusty as quickly as regular steel. And notice it's got a slightly different mixture in that stainless steel. It contains carbon, iron, and nickel. Brass is copper and zinc. And, okay, I've made a mistake there. I should say bronze. Bronze below is copper and tin. Very important in the history of humans. Apologies for the mistake. I should say bronze. Solder and white gold. Well, we don't need to know what they are, but I've just added those just for extra information. Let's go back to our biscuit model and let's see if we can explain how that works. So here's our pure metal. So how are we going to mix the metal with another metal? Well, first of all, we have to make our first metal molten. We have to melt it. We need to add lots of heat energy, overcome those electrostatic forces of attraction and melt it. And then we can add our second metal. Now notice it's a different type of atom, And we can show that by having a different type and different size of biscuit. Okay, so we're going to melt that material. Here we are. We're going to add the delocalized electrons just in the same way. Okay, I'll add another metal atom here. Now, we've got two different types of metals now, and that's shown by the different sizes of biscuit and the different types of biscuit. Notice I'm just keeping the model simple by having one delocalized electron in this model each. So they're still positive ions, and these electrons are still free to move. They are delocalized. So metal alloys also conduct electricity. However, look what's happened to that regular structure. Look what's happened to that beautiful lattice we had before. It's now been what we call disrupted. It's been disturbed. It's been changed. The best word really is disturbed. That's the word we're going to use. So although metal alloys conduct electricity, this forming of an alloy means one of their properties is changed. Where pure metals are soft, because the layers slide across each other, if we try to do a similar thing, it's more complicated. Hopefully you can see that more of the structure is being moved. It is much more difficult to bend, because when we try to slide a layer, lots of other parts of this metal will resist that movement. If we try to slide across here at the bottom, you can see, hopefully, that many other metal atoms are moving. Now, in reality, with all these billions and billions of atoms, that wouldn't actually happen very easily. As a consequence, metal alloys are not malleable. They need much more force to bend those metals, much less malleable than pure metals. So we say they are hard. We say they are hard in comparison to pure metals, which are soft. So pure metals are very soft because the layers can slide over each other easily. If you add an atom of a different element into those layers, it will have a different size, different atoms of different sizes, and therefore it will disturb that layered structure. It will disrupt that layered lattice. However, it will still conduct electricity, and it will still have many features common to pure metals. Okay, hopefully that model helped. What I'd like you now to do is to try and answer these questions which I've taken from an exam. The numbers in brackets indicate the marks for each question. So when you're ready, please pause the video and have a go at all these 4 questions. Come back when you're finished. Welcome back. Let's go through those answers one by one. So check your work, annotate, underline keywords that you've used to get the right answer. If you haven't got the whole answer, add those key ideas and keywords to your answer. Firstly, explain how electricity is conducted in a metal. To gain full marks, you must include a description of the structure and bonding of a metal. So let's do that first. Metals are a giant lattice structure. They are formed by metal ions. Again, we could use the word atoms. I prefer ions. And those metal ions are surrounded by delocalized electrons. And the question was about electricity, so we need the next bit. The electrons can move through the lattice or move through the structure to carry a charge or to produce an electrical current. So each of those sentences would be 1 mark. Check your work. Mark it out of 4. Moving on, next. In a pure metal, there are regular layers of ions, but in alloys, different sized ions disturb the regular layers. In pure metals, there are regular layers of ions which can slide past each other, but in alloys, different sized ions disturb the regular layers. Now, the bit in brackets isn't essential. It's not really related to the question, but it's extra information. So we need at least the idea of regular layers being disrupted in an alloy. Next. Suggest one reason why coins are not made of pure copper. Do not give cost as a reason. Well, pure metals, including pure copper, bends, or you may have written is soft, or is malleable, or is not strong enough. Finally, this is an interesting question. You need to relate the particular feature or property to a different aspect of the metallic structure. We're talking here about iron. So, how does the structure and bonding of iron allow body panels to conduct electricity? Well, within the metal lattice, there are delocalized electrons which carry charge and are free to move in the lattice. The ions are in layers and can move, slide, or slide past each other, and that explains why the body panels can be bent into shape, what we call malleable. However, we used to recognize that if they are malleable, they are still strong. It's still a strong metal. It's still solid at room temperature. And that strength comes from the strong electrostatic forces between those ions and the delocalized electrons. So if you got all those right, well done. Notice we're linking different features of the structure to explain different physical properties. Again, the emphasis there is on the keywords. Okay, so today we've looked at metals and metal alloys. We've hopefully now had an idea of the bonding within pure metals and also within metal alloys. And we've used those ideas so we can describe and explain properties of metals and indeed metal alloys. Let's just do one final task for the end of this video. In summary, if we have some atoms and if they are going to interact and bond between them, if there is a metal and a non-metal, then this will form an ionic bond, ionic bonding, ionic structure. If the two atoms are non-metal with a non-metal, that will form a covalent bond. And finally, as we've seen today, if we have two metals, we mix them in an alloy, that will form then what we call metallic bonding. There are three types of bonding you need to know about: ionic, covalent, and metallic. Finally then, I would like you to complete this table. Either write it down in your book or fill it in your booklet. I've done the first two for you. We have a sodium metal with another sodium metal atom to form metallic bonding. The second one, we have two non-metal elements. These are in the top right of our periodic table, and they form covalent bonds. So let me ask you then to do the remaining 7. If you need to go back to the previous slide, just rewind the video and fill in the table. Come back to the video when you have finished. Okay, hopefully you found these fairly simple using the rules on the previous picture. Carbon and carbon will form a covalent bond. Oxygen and lithium, we've got a non-metal and a metal, ionic. Here we have silver and fluorine, ionic, and magnesium and chlorine, ionic. Magnesium and calcium are both metals. They will form metallic bonding. Beryllium is a metal, nitrogen is a non-metal, so this once again is ionic. And finally, two non-metals will form a covalent structure. Well done if you got all those right. Hopefully you found that useful today. Thank you for watching. See you next time.